Well, this work was done some time ago, so some of you probably have seen it, so sorry for that, but I think this is interesting because it has some interesting mathematical features that actually motivated some further studies, in particular the ones that were reported by Negre and by Fabio some time ago. So today I will be talking, well, since I'm from IMPA, I will be focusing on mathematics. So I will be talking about mathematics. Of course, I will make connections to applications, to industry and so on, but I would like really to talk about more mathematical side, also because it's quite curious in that case. So we're talking about combustion wave profile. Everybody knows that, well, you have a traveling wave, how to find a profile. You go to the frame, coordinate frame moving together with the wave, so the system reduces to ordinary differential equations. So there is two extreme states of the wave, which are fixed points, and so you need to find a heteroclinic orbit going from one fixed point to another fixed point, and that's it. So it turns out that in this case, it's much more curious than that. And actually, the profile comes from one fixed point and should go to the intermediate fixed point, and then from the fixed point to the last fixed point, and somehow it doesn't stop forever in that intermediate fixed point. It passes it through. And, well, it's not directly clear from what I said how it can be possible, but it's really possible, and more than that, it is robust. So I'm going to talk about. So this is the beginning. You've seen this slide already. So what's the motivation? Motivation comes from oil recovery, so we need to recover oil. And we will be talking about in-situ combustion, so this air injection, which leads to creation of the combustion wave. Well, the combustion, in-situ combustion, we need to increase the temperature, and usually it is applied to the recovery of heavy oil, because heavy oil is very viscid, so it doesn't move. Combustion increases the temperature, decreases the viscosity, so it moves better. So this is very old and very clear motivation. We will be looking at the in-situ combustion of light oil. So this is kind of strange, why we need combustion with a light oil, because light oil already has low viscosity, already moves. But still, the motivation comes here. So already in the talk of Pacelli, he showed that even with the improvement of the recovery of the method, we recover more or less half of the oil until 60%. So even a light oil reservoir, half of oil is left behind. So we have half oil left behind, and the in-situ combustion is a method who has a potential to recover the rest. Okay, the potential is a key word because, of course, there's a lot of work to do it to know to what extent it can do it, but it really does, even in experiment that I'll be talking about. So it's in-situ combustion for light oil. It's not the increase of temperature that is not the effect of temperature to viscosity what's important, but what's important is the vaporization condensation mechanism, which really creates a wave which can clean up the reservoir. So this is the motivation. This is also the slide I think was shown by Negre. The message is the following. So there are two types of, essentially there are two types of reaction. One, high temperature oxidation happening in high temperatures. And this is usually based on the fact that at these high temperatures, the oil cracks. It leaves some heavy, or some solid reminder, the coke, and the coke is reacted. And at lower temperatures, coke is not formed, so really reaction is with a liquid oil, or it can be in a liquid or gas phase. There is a kind of dispute about this, but we assume that it's in liquid phase. So, okay, so let's come to the mathematics. So this is a model. We have one space dimension, x, time, and five variables, 5 dependent variables, which is saturation of the oil, velocity of the gas, two components in the gas, which is oxygen Y and gaseous fuel X, and temperature T. So we have five equations. So the 4 equations for the mass conservation and 1 equation for the energy. Well, we make it as simple as possible. It doesn't look that simple, but we neglect all diffusion effects, heat losses, and so on. But this is still more or less fine. So then we consider the one-dimensional medium filled by oil. So this is liquid fuel, and we inject air, and everything is described by this system of balanced laws. And the so left-hand side is the conservation part, and the right-hand side is the source term. So the reaction, WR is the reaction rate, and WV is the vaporization rate. So we assume that there is a reaction and vaporization condensation depending on the sign. So we have these kind of terms. Well, so out of the structure, it's clear that the right-hand side, which is what makes it difficult, so we have the source terms, but there are only 2 source terms, WV, WR. So we can keep it in these 2 equations, but in the rest, we can substitute it from these 2 equations, substitute in the others. So we will finally we have 3 conservation laws, which are just purely conservation laws, and 2 balance laws, which has the right-hand side as a source term. And what will help a lot is that we have a small parameter in the system. Well, everybody's always happy when he has a small parameter. So in our case, it's related to the fact that vaporization in a porous medium, these kind of problems when the pores are small, is way much faster than oxidation, than the reaction. So the vaporization is much more faster than reaction, and epsilon is a ratio of characteristic reaction rate to characteristic vaporization. So it's very small, it will be used. We have initial condition is, for example, the reservoir with filled by oil, so S is 1, and we can bound the condition which determine injection. So we inject air in the reservoir. So that we come to mathematics. As I already mentioned, we go to the coordinate system moving with the wave. So V is the speed of the wave. This is just simply some notation. So it turned out to be all formula look much nicer if we use fluxes instead of variables. So we use total flux, gas flux, and oxygen flux. So then when you come to this system, you reduce to the system of ordinary differential equations. Well, the conservation laws can be integrated directly. So we have algebraic equations. And balance laws, they become 2 ordinary differential equations. So we have 5 equations, 3 algebraic and 2 ordinary differential equations. And we have, since it's traveling wave, we have 2 limiting states. One state at the minus infinity is a burned state, and unburned states at plus infinity. So there are several unknowns, and also the speed is unknown. So what we need is to find a solution which satisfies these equations, these conditions. So this is a kind of more or less classical idea. You have 2 states at plus infinity, minus infinity. It's automatically fixed point of the system. But the difference is that we have an algebraic and ODE part of the system. Well, it's 5-dimensional space. Actually, 2 equations are linear, so they're resolved simply. So essentially, we have 2 ODEs on a surface described by this system. And surface looks like this. So the surface, this is 3 dimensions. So we have ODEs in the plane, and the ODEs, they are determined on the surface defined by the system. And it turned out that the surface is not just flat, it's folded. So you have an ODE determined, the ODE you determine on the projection. So the surface, if you project it, you have an ODE. But the problem that you immediately see that there is a problem on the fold, because the fold is related with a single vector. And if the vector is not tangent, you can't go from one side to the fold to another side, because they look in the same direction. So the fold is kind of forbidden line. It doesn't allow you to go from one side to another. So this is one peculiarity. Another peculiarity is the following. So we have burned state, unburned state. So it turned out that burned state lies on this axis. So this is minus state. And unburned state lies on this cut of the surface. So it can be either above the fault or below the fault. So we need to find an orbit which comes from some point on this axis to some point here. And I already going forward, I will tell you that the physical solution corresponds to the plus state at the upper part of the surface. So you must cross the fault. You must cross this forbidden part. And it's already, as I saw, that you cannot cross the fault in any point. You can only cross the fault in a very specific point when the vector field is tangent. So you have something kind of singularity. So it's already clear that to go from a minus state to plus state, you should stop in the singularity in between. So what we do, first of all, we take, what is shown as we will look at this fault from a side. So this is kind of a nice way. So we look at it from a side. So this gray part is the lower part of the fault, and white part is the upper part of the fault. We can take make use of the fact that we have a small parameter. We just send this small parameter to 0, and then the vector field on this folded surface is just what is shown here. All curves are vertical, and these curves just simply determine the vaporization mechanism. It's very fast, so this is related to vaporization. Just nothing changes except that the immediate vaporization happens. And then there is a special curve here, which corresponds to thermodynamic equilibrium. So there is no vaporization on this curve. This is the system. Well, and we immediately can find the solution. So one solution is if we want to go to the point, if we don't want to cross the fault, we can start at the point, go until the equilibrium curve, and then follow by the equilibrium curve to the plus state. So this is a connection. Of course, this is for epsilon 0. If epsilon is slightly bigger than 0, it will be smooth, so it won't be an angle. So it will go like this. And there is multiple ways how to do this. So you go to any point and then go to plus state. And there is only one way how you can go up in the upper part of the fault. So you have to come to this very specific point. And the only way to cross the fault, you cannot cross the fault here, you see, because it's going in opposite direction. So you go to this specific point, and then follow the equilibrium curve to that plus state. So plus state is fixed, and also this minus state is fixed in that way. From a physical part, you first have vaporization. It's very fast vaporization to this singular point, and then you go along the equilibrium curve. So this is what happens. And so this point is important, and at this point we have a singularity condition. You can check what this point means, and you derive directly the fact that the speed of your wave should be equal at this point to the characteristic speed of the flow. So this is what we say resonance condition. So the speed of the wave is equal to the characteristic speed of the flow. It's determined at this point, and this is an extra equation. In a sense, this is a simpler situation to what Bradley was talking about saddle-saddle connection. When you have saddle-saddle connection, you should adjust a parameter to make a connection between the two sides. And it gives an extra condition. So in our case, this point gives an extra condition, and this is the extra condition which determines the speed. Without this extra condition, we cannot determine all the parameters of the wave. So this all structure could be proved analytically. So there are proofs of these all facts. And now PT of epsilon, we take epsilon slightly positive. And what happens is this singularity, it open up. So we have situations something like this. So this actually becomes a clearly the saddle point singularity of the vector field, but this saddle point lives on a fold. It's exactly on a fold, and it represents a saddle fixed point. So there is one curve which enters and one curve which exits. So, and again, we can prove that this point is determined by this resonance condition. So the speed of the whole wave equals at that specific point to this characteristic speed of the flow. And there is unique orbit which connects some minus state to the very specific minus state to very specific plus state. So everything is kind of frozen. And this whole construction allows, of course, you to find a unique wave speed. In a while, I will mention that this is a very generic situation for some class of the systems. And well, this is peculiar because you start in a fixed point. You should visit another fixed point in the middle and go to the third fixed point. But this is kind of fake fixed point because you come, since it is on a fold, you actually enter in a finite time and you exit in a finite time. So you actually, it is a singularity, but you don't stop here really. Since it's on a fold, you can show that you don't stop forever as you stop in a fixed point. You just pass it in a finite time. We looked at the literature where this situation appear, and it is quite curious. So first of all, it is generic, and physicists know about this. So we found it's rather seldom. Okay, it's not typical situation. In a very well, it is either happens rarely, or it is simply, since it is something more complicated, we don't notice in many cases. Probably we don't know all the cases where it can appear in other systems, but what we found out is that it appears in some detonation problems, which are kind of complicated detonation problem when there is a series of reactions happening together. Then it was happening in astrophysics in some supernova explosions, so it is pretty curious where it happens. So the petroleum engineering provides a new case, and mathematically it's also not very well studied. There are some relatively recent papers in the last decade considering this situation, but I think that still existing uniqueness of this and rigidity of this situation is to be studied. So this is the two cases. So we have two cases, one connection and another connection, two types of connections. This is the profiles which correspond to both of them. And the most interesting, as I said, is one which goes from, this is a saturation, one which goes from zero saturation to high saturation, which crosses a fault, and another goes from zero saturation to lower saturation, which doesn't cross the fault. So we will say that this is a interesting wave. So this is a combustion wave which doesn't leave any oil behind on the burnt side and leaves quite large saturation in the unburnt side. There is a temperature profile which goes down, it absorbs, oxygen is erected, and there is a vaporization, so there are different curves. And also, we see that we have vaporization region, so this is a singular point, so this singularity corresponds to infinite derivative of the saturation profile. So the saturation profile has this infinite derivative, so it's really singularity. Before the singularity, we only have vaporization, so it's vaporization region. And after the singularity, we have a reaction with a slight condensation. So really the resonance point separates two very different physical regions. And well, what Hans always found to be counterintuitive, so much that now I also find it counterintuitive, is that vaporization goes behind the wave. So the combustion wave goes to the liquid, but liquid does not vaporize in front. It's actually vaporized behind. And what in the place where it meets liquid, it condenses. So it takes, it vaporizes behind, brings this vapor in front and vaporizes it in front. So there is always kind of sequence that it takes vapor from behind and put it in front. So that's how it creates also this high saturation in the front part. So this is kind of this is just a simply numerical example. Well, for this numerical example, we can compute everything, including the speeds, profiles, and so on. For this, interestingly, that the saturation in front of the wave is fixed. It's not determined by initial condition, initial state of the reservoir. It's 0. In that case, it's 0.4, but in many cases, it's larger, 0.6, and so on. So the wave itself creates a level of the saturation of the oil in front. It doesn't matter what you leave in front, it will create a fixed number, exactly by this mechanism. And also we found that this different kind of solution is really uninteresting. It only happens if you if the initial saturation of oil is below the 1%, so it's certainly out of interest. So all the interesting physical solutions are those who go through the fold and pass through this singularity and satisfy the resonance condition. Okay, so the next, what we also did is we considered, well, we know the structure of the combustion wave. Now let's see what the whole solution looks like. So we need to solve the kind of Riemann problem. This was done, and we showed that the solution has a unique the problem has a unique solution as soon as the saturation of oil is bigger than this 1%. And the solution has 3 waves inside. One is a thermal wave. It's well, we don't have a diffusive term, so it's just a shock. Then we have this combustion wave, and combustion wave has a very specific saturation in front of it, which is a property of the wave itself. And then goes the saturation. This is Bucklet-Leverett wave, which is normally a rarefaction plus shock, so something, this displacement. So this is the full solution, which we know. And from this solution, we can, as an application, we can draw the recovery curves. So what happens is you inject air, it creates combustion wave and saturation wave. So first, if you see what you recover on the right-hand side, first you will see this wave. So first will be a wave, the recovery as it was in gas displacement, and then comes the combustion wave, and then you will recover this section at the fixed saturation. So you will recover at the constant rate, which is also very nice. So these are curves. So this blue curve is really the Bucklet-Leverett recovery. And as I mentioned initially, you only recover little. You recover 40 to 50% of the oil. So you see when it becomes 40%, the curve becomes very shallow. So you inject gas but almost recover nothing. So that's why always the recovery stops here, because it's not economical anymore. And with the combustion wave, what happens is at a certain moment, the recovery continues as a straight line. And as I said, a straight line is because the plateau is constant. So you get a straight line. And depending on the pressure, the straight line detaches in a different point. It's really not interesting to recover anything at 1 atmosphere. But when you come to the pressures which are typical for reservoirs, 10, 50 atmospheres, it becomes really interesting. And it recovers, well, theoretically up until the 100%. So this is the recovery curves, and these are for different type of oil that we considered, like lighter oil, medium oil. The situation is very similar. Actually, it's self-similar. It's you can see that the horizontal scale is different, but the whole picture looks very similar. We did numerical. Actually, it was mainly the work of PhD work of Neger, which did both numerical simulations for the recovery, actually in a much more advanced model, including all the diffusion effects, water phase, and etc., and also laboratory experiments. And what was found is really the theory agrees very well with both numerics and experiment. So first of all, we have this gas displacement with very steep. So this corresponds to this part. The only difference is that there is this intermediate section. This intermediate section, when we almost recover nothing, it corresponds to the fact that combustion wave needs some time to start. So it's ignition period. So ignition, well, if we consider very large reservoir, this ignition period becomes smaller and smaller related to the other scales, so it will disappear. So there is between the blue curve and the red curve, there is some ignition period that we see numerically, and then it starts really the recovery with a constant speed, where the mechanism is a combustion wave. And qualitatively, very similar stuff we see in experiments. So it's first there is a steep part with a gas displacement, then there is ignition period, which is almost no reaction, and then the long part where we recover everything with a combustion wave. So now I'm coming to the conclusion. So what we have is we found that the combustion wave can be well, we believe that it can be a very useful mechanism for recovery of light oil. And of course, we don't need to decrease viscosity of light oil. The viscosity is already low enough, but the other properties like condensation and vaporization act together with the flow in such a way that they create a wave displacing the oil at the constant value of the oil saturation, like normally 0.6 that we've seen. So can be very efficient. Mathematically, it's pretty curious. We were curious to see this connection. So to find a traveling wave, you cannot just connect one fixed point to another fixed point. First of all, you're on a manifold. Manifold is folded, while the ODE is determined only on the projection. So you have to pass through the fault. You cannot pass through the fault in any point. Then you find out that you should pass through the singularity on the fault. And this singularity gives extra condition, which is a resonance condition. And altogether has to be taken into account in order to determine for example, the wave speed and all other parameters. And then we found that there is a uniqueness of the solution in the form of the traveling waves. And really, this solution includes the combustion wave exactly of this type with a singularity in the middle. So there's some publications, and well, thank you very much.
Question?